All right, so hello and welcome everyone to today's Social Science Data Lab. My name is Dennis Cohen and I am happy to welcome you to today's talk by Marcel Neunhoeffer on Generative Adversarial Networks. The Social Science Data Lab is an event series at the Mannheim Center for European Social Research, where we provide a platform for early career scholars to present tools and methods for the collection, management, analysis, and visualization of data in the social sciences. The Social Science Data Lab is organized by myself in collaboration with my colleagues Cosima Meyer and Julian Bernauer, with the support of our student assistant, Nick Baumann. So our speaker today is Marcel Neunhoeffer, who is a PhD candidate and research associate here at the University of Mannheim. Marcel's research interests include the application of deep learning algorithms to social science problems, the prediction of political behavior and election outcomes, as well as the ethical implications of new trend in applied social science research like big data and AI. In his talk today, Marcel will talk about generative adversarial networks, which is an innovative neural network architecture where neural networks adversarially learn arbitrary target distributions. Marcel will feature applications of GANs to multiple imputation, small area estimation, and the generation of synthetic data. Before we start, and before we give the floor to Marcel, here are a couple of reminders on the logistics for today's session. You may ask questions at any time during the talk, and there's 3 ways how you can do this. You can post comment or question or whatever in the Zoom chat, and we will then call on you and ask you to unmute yourself and speak whenever it is convenient. You can post your questions publicly in the chat, and we will read them out with your name or with mention of your name. Or you can send us your questions via direct message in the Zoom chat, and we will read them out anonymously for you. Once again, the disclaimer: we are recording the session. We're recording it in active speaker mode, which means you will not be recorded unless you unmute yourself and speak. If you unmute yourself by accident and want to be edited out after the fact, please let us know by shooting us an email. So with that being said, Marcel, we are very happy to have you here today, and the floor is yours.
Yeah, thank you, Dennis, and thank you to the Social Science Data Lab for inviting me. I'm not quite sure what happened in the planning of today's date. I'm sure there's a couple of people in the audience that just like me didn't sleep too much last night. I have all my notifications on mute, so whenever there is some world-changing events happening, let me know, or you just leave and I will stay and continue with my talk. So I, as Dennis introduced, will present generative adversarial networks for social scientists, which also happens to be the topic of my dissertation. I hope you can all see my screen, and I just need to make sure that I can also see you, and that window just moved with Zoom, but here we go. And given the audience, I tried to give you a good overview about what generative adversarial networks are. And some of you probably have seen them in action before. I guess at least you've seen the first few examples that I will show in a second. And then I think it's important to understand these neural nets to actually make sense of what they're capable of. And what is more, and that's actually the interest of my research, is how can we find clever applications to social science methods problems so that we can actually use them in our method toolkits. All right, so as an easy introduction, there's nothing better than cat pictures on a day as today. the thing is, and like the title gives it away, right? So these cats do not actually exist. And if you get the slides, and I assume like those slides will be made public via the Social Science Data Lab GitHub page, you can click on the link and you can generate like an arbitrary number of cats. These cats I actually not really dreamed up, but like learned by an generative adversarial network. So like this artificial intelligence, as it would be probably described in media, gets to see a lot of cat pictures and then learns to generate new cats on its own. And if you look closely, like the eyes somewhat look too good to be true sometimes. And actually that's like one of the things where those synthetic images are still giving themselves away in a bit, like so if you look closely, you can actually see that they are probably not real, but like synthetic. But nevertheless, those cats are cool and very cute. What's a bit more problematic or scarier, like, so there's nothing to restrict those networks to only learn cats, right? So they can actually learn anything, like they will be trained on. So you can also dream up persons. And they look pretty realistic. So that's, of course, not the output of my research, but that's like Silicon Valley companies like NVIDIA and Google and Facebook who are investing a lot of resources into generating such images. So like just as a benchmark, like that me or we as junior scientists could probably never come up with a cool neural network to generate these things. Like those networks were trained for the equivalent time of 52 GPU years. So if you only have one GPU, right, that means that you would have to train your model for 52 years. And I guess the guys at NVIDIA, they have quite a couple of GPUs, so they can train it like probably in a day. So that's what GANs are capable of, but just to curb the enthusiasm a bit, it's probably not what we could do from scratch. But that's not so important as you will see. What's also possible, of course, is to generate videos and sound. So basically, you can train those networks, like instead of giving them cat or images, like portrait images of people as the training data, you can give them like sound bites, or you can give those networks video sequences. And like what you can do then is you can actually generate text, like spoken word from text. And let's just try this out. So I have the link up here. And down here is the live demo of the tool. So we are learning about generative adversarial networks in the Social Science Data Lab. Cool stuff.
We are learning about generative adversarial networks in the Social Science Data Lab. Cool stuff.
And you can actually choose like other voices as well. So maybe we would like to have a male.
We are learning about generative adversarial networks in the Social Science Data Lab. Cool stuff.
So that's pretty awesome. And actually the business case, like this startup from Canada is making is pretty awesome for everyone who's teaching remotely right now. Because they basically offer a transcription service that transcribes your videos, and then you can just delete all your ahs and ums and in-paint like the words that you wanted to have there, and it will just seamlessly integrate like with your own voice, which is like super awesome, but also super scary. Like, like that's about the ethical implications of this research that are very real. And also in the past election cycle in the US had actually some impact there. And it's also the first reason, I think, why we should care about these generative adversarial networks, like why we as social scientists should care. This is a technology that potentially like impacts how we can assess video and like audio and images. And potentially in the future, those networks might be powerful enough to generate like super realistic looking images and videos that might be problematic. And therefore, I guess, for us who often also use those data sources for our own research, it will be really important to know that like synthetic videos and pictures can exist. And hopefully maybe also think about how we can detect them or how we can come up with like ethical guidelines to like prevent the misuse of such a technology. So, and that's actually what happened in the like election cycle in the US. So I guess you probably, if you followed the news, you heard about like this Hunter Biden scandal, right? That he had some business partner in China and like wanted to introduce those business partners to his father. And it turns out that like this is the guy who apparently is like working for some intelligence firm. So it sounds a lot like those infamous Steele dossiers from like the 2016 election, you know, on the other side. However, like this person doesn't exist and this photo doesn't exist, right? So like they even concealed like all probably traces, like if you take a photo of someone, right, you can probably trace back to where the photo came from or where it appeared the first time. And use the fake photo on the Twitter profile of this like supposed security engineer who wrote this dossier about Hunter Biden. And it's of course not just a fake image, like they made up a whole fake persona, and also probably like the story is also very fake. However, with this, they tried to give it legitimacy and like tried to land it in actually major news outlets, which luckily all like didn't want to publish the story, with the exception of the New York Post. Another thing, and that's probably even scarier, is like the creation of those deep fakes with like realistic sounding voices. And actually, Lyrebird AI is like the firm or the startup that was behind like this video transcription service, or like before they renamed themselves and before they found like a probably cool and sustainable business model. That's what they plan to do. And they use like a video of Barack Obama, and this is now 3 years ago, to show like the potential and also the potential threat of their technology. So let's just listen to a fake Barack Obama for a minute.
Hi everybody. This night I am happy to share with you a small announcement about a cool startup called Lyrebird. They launched today their website where you can create a digital copy of your voice. They only need you to record 1 minute of audio. This is just the beginning, and they are working hard to improve their results. They want to use this technology to change the life of everyone that lost their voice to a disease by helping them recover this part of their identities. Let's help them achieve this goal. You can help them testing their software and sharing this video with your friends.
All right, so we don't want to watch like an actual live bird. So that was like the promotion, like the first promotion video, like that they used to make a big buzz about the technology that they have, right? And I guess for us as social scientists, as political scientists, it's not really hard to see like the potential threats of this kind of technology, right? And now this was 3 years ago, and you've just heard like how like their technology developed in the last 3 years, so that you can really create realistic sounding like voiceovers from raw text, and even train it with your own voice. So like that's the safeguard they build in, like you can only train it on your own voice. But of course, if you come up with like a sophisticated like setup, you can probably also train it on some voices that you find on YouTube or like on a podcast or something. So that's why we should care. Like we should care to understand how these things, how these artificial intelligence technologies work, to make sense of those potential threats. And I think the best way of like to get a feel for what's happening there is actually to look at how it is done, at least on a lower level that we can train on our own machines. So that's the one side of why we should care. And the other side is, and that's what I will also cover in this talk, is that we can actually use this technology for applications in the social sciences, like to enhance our methodological toolbox. So since this is a how would you describe it? It's a artificial intelligence, a neural network architecture that tries to mimic arbitrary target distributions. Those were like the first things that I came up with for my dissertation. But I'm sure that there's many, many more applications that you can come up with. Maybe you're inspired to a clever application by this talk, and that I'm happy to discuss and talk about like at any time. If you think like, wow, like I have a very cool idea, please feel free to interrupt me anytime. So the first thing is, of course, where we want to draw from like target distributions that we want to approximate like very well is like for things like sampling missing values, as in multiple imputation, right? Where currently the state of the art is to use either like Amelia, which would be, or which would try to approximate your like missing values from multivariate normal distributions that you can approximate by arbitrary linear regressions, where you could also include more complex functional forms. But in the end, what it will do, it will draw from a multivariate normal distribution. And a bit by extension from the application to multiple imputation, another another application where we usually want to draw from a target distribution that we don't actually know, but where we can like approximate it well with like with other variables, or like where we have some target that we can learn from, is a small area estimation. And actually, the way I set it up, it's really just an extension of multiple imputation. And the last thing sounds probably like the fanciest, and it's not that common in the social sciences yet. So you could, of course, also try to use this technology to synthesize entire data sets to protect the privacy of individuals in your original data. So for example, if you collect data on individuals that you have to upload to a replication archive because you want your article published, but at the same time you ensured, or you like guaranteed all the participants of your study that their data will never ever show up anywhere, and it will just be on the University of Mannheim servers forever. this is a potential way forward where you can then actually share a synthetic copy of the data that will allow other researchers to like run your code and in the best case even get similar results that you had in the original analysis without actually sharing the raw data. And as I said, there's potential for many, many, many more applications. And I'm pretty sure that there's also like the potential for applications with cat pictures in, like with synthetic cat pictures in the social sciences. All right, so let's dive into the technology. And this will be a really, really brief and hopefully not too technical introduction. Like I'm happy to talk more about it in the Q&A, or whenever you have a question, please also let me know. So this technology first came up in 2014. It was developed by a group of like researchers in Canada, where Ian Goodfellow, who did his PhD back then, was like the main person behind the idea. And basically, it's a surprisingly simple idea. So at the core, it is really just a minimax game, like which some of you might have heard of in like classes like game theory, or maybe also in your methods, like in your statistical methods classes, where we have two competing actors, a discriminator that we will denote by D for the rest of like the slide deck, that is trying to tell real from synthetic samples. So basically you can think of it as like if you have two groups of people where you have one group trying to forge fake money. That would be the generator, which is the second actor in our setup here. And the police, which would be given real and fake money, and then would try to learn or would want to learn to perfectly distinguish fake from real money, right? And with the feedback of the discriminator, so the discriminator tells the generator, well, what you gave me was fake, or what you gave me was real. With that feedback, the group of forgers can learn how to produce more realistic looking money, like at each turn, basically, right? So the generator is trying to produce realistic looking synthetic samples from random noise. So in the end, it will be a neural network that gets random noise as an input and outputs like cat images, images of persons, or in our case, data points from a distribution that we care about. And formally, this is just can be written down as any two-player minimax game, where we want to have want to minimize this term for the generator, and the discriminator wants to maximize this term, right? So the discriminator always wants to be able to tell the difference from what is given by the forgers and what is given by the real data generating process. And of course, the group of forgers wants to confuse the discriminators as good as possible. And in the end, since this is a min-max optimization, right, this will not converge to a maximum or to a minimum, but it will converge to a Nash equilibrium, like where the two cannot improve like by a lot over the other anymore. So in theory, that would be the point where anything that the generator presents to the discriminator would get a probability of 0.5 of being real, right? Because then like the discriminator couldn't distinguish what's real and what's fake anymore. And because there is no feedback anymore, the group of forgers also couldn't learn anything useful about how to even make it better, right? And in theory, that like equilibrium can be achieved if you have like a discriminator and a generator of infinite capacity. So that can be shown that this equilibrium exists in theory, but of course in practice we never have those. But as you've seen with the cats and persons, even if we don't get to the equilibrium, we can get scary, real-looking examples from such a setup. So there is like this F in here, so there's like different ways of how you could parameterize this in the loss function or in this min-max term here, where you could use the log for F, and then this would really just be like the likelihood for a logic model, right? So for binary classification. And if you use like the identity, this would be to minimize the Earth mover distance or the Wasserstein distance between two distributions, two probability distributions. And right, so those are the other terms that should be in there. That's a more like simplified view on what this will look like in the end, where we have those two modules, like the discriminator in red and the generator here. And you can see that the generator actually gets just a batch of random noise. Then depending on the task you want to tackle, you have a network architecture that can then output, for example, handwritten digits here. And then real, and that's what's coming from the training set here, real examples and fake examples are fed to the discriminator, and the discriminator should then tell whether this is real or fake. And also here, of course, like the architecture of this network depends on like what kind of input you give it, right? So there is lots of research on visual recognition tasks, for example, and if you want to do something with images, like those convolutional neural net architectures work really well here. And that's also what is depicted here. All right, are there any questions so far? If not, let's actually look at some code and try to implement GAN ourselves, where you will get access to that code as well through the Social Science Data Lab GitHub page, but since it requires some Python and Conda experience, I didn't want to share it before, because then it would just confuse probably everyone and make your lives hard, because it can take a while to get it to run for the first time. At least that's my experience with it. So you will get access to this code, and feel free to ask anything like why we go through it, and also feel free to, if you want to get this to run afterwards, after the Social Science Data Lab today, feel free to email me, and we can or I will try my best to get it running on any machine. So the code should be very portable. All right, so you can see this is actually our code, and I will use the reticulate library to call Python functions within R and do like the training in R. So that, yeah, like the main reason is that I'm just way quicker by doing this in R instead of Python natively. And also like the big learn for me was that it's really, really easy to actually use like those Python network architectures that you get from like those state-of-the-art papers from the leading computer science conferences, even in your like usual work environment. And hopefully that's, I'm not the only one who thinks this is really cool. So this will just make sure that we all have the same packages in R. And then I will also include instructions of how to, and what to include in this conda for the GAN Social Science Data Lab. What you will need is PyTorch, which is a like neural net, open source neural net library for Python that makes it really easy to like design your own neural nets and train them. Then NumPy, and that's mainly used to convert Python data types to R data types in here. And then we will just, for convenience, we define some submodules of Torch so that we can easily access them in here.
Hey, Marcel, sorry to interrupt.
Sure.
Could you please increase the font size a little bit? People are having trouble reading this.
I can.
Thank you.
Is this better? Cool. And so with Reticulate, this is how you can source arbitrary Python scripts. And we will look at this Python script while our GAN runs in the end. So this is where we will define the network architectures in Python so that we can make use of Python classes. So since usually we don't want to learn cat images, but maybe like more like data like this, right? This is like a simple toy example that should motivate like what's going on and should also make it easy for everyone to actually see what's going on. So this is our true data. This is our cat images. So each, like you can think of each of these data points as like an image in the other setup. And what we want to learn with our GAN is exactly this data distribution, right? So how can we set up our GAN? So we need a generator, and I will show you what this generator is. So that comes from this Python script that we just sourced. And the rest is really just PyTorch particularities that you need to send it to like the device of your computer, like the GPU or the CPU where you want to train this. You need to define an optimizer for your generator net. That's what we do here. So basically this is the equivalent of doing like if you ever have done or written your own maximum likelihood estimators, if you use optim in R and specify BFTS or some other optimizer there, that's basically the same thing for neural nets, which like we will use to make like to train like the weights of the net, which is basically the coefficients in our neural net. And we do the same thing for the discriminator. Then you need to, so in PyTorch, like all the weights are initialized to 0. So usually that's not really helpful, as we also know from maximum likelihood. So you can use an init weights function that will randomly initialize all the weights in the net. And then here we just send our data to like the PyTorch device that we want to train on. Or first we convert it to like a PyTorch format, and then like here we also generate our noise sample that we will feed to the generator. And this will be one fixed noise sample so that we can observe the training. Then we will just quickly define a function And this will be way better commented in like our Markdown script that you will get access to. However, I didn't get that to work for some reason, so I will have to live with my comments for now. So this sample synthetic data function will pull out like generated examples after we trained the network, and transform it to an R object so that we can actually use it as usual, like R data frames or matrices, so that we can plot it. Then we actually are already, so what do we have now? We have like a generator net, we have a discriminator net. We have an update rule for each of these, like how to train those like weights in the net. And now basically we can get started to set up our training loop where we, for each iteration, will calculate these loss functions that we've seen for the in the technical overview of the GAN. And then we can backpropagate this loss and use this optimizer to actually update our weights. To do that, we need to set some hyperparameters for training, where one is the batch size usually. So how many of the training examples do you pass to the neural net per update step? And this is, for this example, that's probably like, doesn't matter much. Like we could also use the entire data. However, if you then work with images, it can get tricky to fit all of the data into your memory at the same time. And therefore it makes sense to sample mini batches of data and use like a stochastic optimization regime. So we use just 50 examples at every step. Then we just want to know, all right, so given our like training data size, how many steps do we need on average to make one pass through the whole data? So that's what I call steps here. And in like the neural net machine learning lingo, an epoch is like defined by one pass through the entire data. So per epoch here, we now have 20 update steps. So in total, we would have 2,000 update steps here for this setting of epochs. But you could, of course, put this to an arbitrary other number. So that's our total number of iterations, just to define, yeah, like actually I could have used it down here then, to know how long we run this. And then we also need an object where we store some intermediate training statistics so that we can actually have a look at our training progress after we ran it, and also potentially during running it. So, and then we have a training loop. So now really at each step, we sample one mini batch of our data, calculate those losses, update the weights, and then we start over again, right? Until like, and since we train at every step, we train both the generator and discriminator, they get better and worse, better, worse, better, worse, until we hopefully get somewhere close to an equilibrium. So how do we do that? We sample data, or at first like IDs from our data set. And then we just subset our X, so that's the data tensor for Torch, where we just subsample like it to the IDs that we've drawn. Then we also need to define our noise vector. So we have two inputs to our GAN, right? We have like the actual data and we have noise, where the generator first generates a fake image from noise, and then the discriminator gets like a real and a fake image to distinguish. And then this is just like the beginning for a training step in PyTorch, so that we don't accumulate gradients over multiple passes over the data. So we just look at the current gradient at each iteration. So then we just calculate those things, right? So we just pass the data through the discriminator net, and what we will be left with in the end. So this should be 50 data examples. So this looks a bit different than what we usually have in R, but not too different, right? So this is 50 data examples from our data set, where we have our variables A and B. And if we pass it through the discriminator net, we will just get a score. And basically these are logit scores right now. And this basically assesses like the confidence or the quality of those samples. We store this as this real, then we do the same thing for the fake examples, because if we split it up like this, it's really easy to calculate all the necessary loss functions after that. For this example, I use a recent development that's somewhere in between like those two functional forms that I've shown you on the slide. That's the so-called using the KL divergence between the real and the fake data. So we just calculate that on the fake scores and on the real scores, and add them up, and that's our discriminator loss. So basically that's, we now want the discriminator to minimize this, right? So that in the end, if this is minimized, it would perfectly distinguish between fake and real examples. And then we can actually use this to make a backward step through our neural net and update our, like with our optimizer. Now we updated our weights a tiny bit. And then we do the exact same thing for the generator, where instead of course, data, we pass random noise to the generator net. So C is really just noise from a normal distribution, standard normal distribution, independent noise. And this gets passed to the generator net, and in the end, the output should, at least the dimensions should match our original data set, of course, because otherwise it would be really easy to tell fake from real, right? We calculate those losses, and then we can have a look at what values we store here. And that's basically the KL divergence between real and fake data after our first update step. And of course, ideally, we want this to go towards 0, because then our network would be maximal, like uncertain about like where those things come from. All right, so let's just run this for a bit. And you can watch the training progress in the plot window. So this is how it starts. And then it hopefully gets better and better. Hopefully just like the election results in the US while waiting. All right, so we do this for 100 epochs here now. Let's just have a brief look at what is hidden in this Python file. And in this Python file, we have just basically what we called as generator directly in our R script. And this is really just the neural net that creates real looking output from random noise, right? So this just starts with so it's a deep network with 3 hidden layers, where we have then those fully connected layers, and in between we can have normalization layers and dropout layers for regularization purposes. And the discriminator net looks very similar. What's important here, if you want to do this with your own data, is that these dimensions have to match, right? So the dimensions of the output, and that's the last number here, so it outputs 2 columns, has to match the dimensions of the actual data, and this has also be the same as the input dimension to our discriminator net. So if you want to train this on a data set where you have 10 columns, this should be 10, and this should be also 10 here. Right? And of course, you could probably write this in a way smarter way where you would directly get this from your input data, the shape of your input data set. All right, so let's go back to our training, like where this seemed, it looks actually pretty cool. After 100 epochs, so we can see how our training did in the meantime. So that's just like iteration on the x-axis and the KL divergence on the y-axis here. And we can actually see that it converges towards 0. We could probably run it for a bit longer, and then we would get like even closer to 0. So now that we have a generator that seems to generate data from the distribution that we were interested in here, we can use it to sample an arbitrary number of points from this distribution, right? So all that you have to do is you have to pass it new random noise every time, and then it will generate a new random point from your target distribution. So that's what we do here. We just loop over creating a number of points. Like basically we create 100 data sets, like fake data sets from our original one here. This will take a little while, but hopefully not too long. Here we go. And that's what we get here. And with this, like with those densities, you could probably also get an like uncertainty estimate for how likely a data point is given like the model that you learned. As you can see, or as we are primed as compared to computer scientists to see, this obviously doesn't really include like any fundamental uncertainty, right? This looks more like model uncertainty if you just use C as like your randomness in the data generation, because like we have real data points that lie outside like this hull where we have fake data points. But this is also what we have in the context of regression models, for example, if we don't include fundamental uncertainty. You could include fundamental uncertainty just as a quick hack by including dropout layers to your neural network. That means that at each training iteration, arbitrary like neurons are sampled that will be set to 0. And with that, the neural net is prevented from like memorizing and overfitting, because in the next iteration, like it cannot rely on this particular neuron anymore, and therefore has to learn higher like abstractions from the data. And if we use that in the forward pass for prediction, maybe we should just quickly, oh, that's weird, quickly do that. No, okay, it won't let me do that. That's unfortunate. But as soon as you have the code, you can try this out and generate data with dropout. And you will actually see this will then reflect also fundamental uncertainty, where we will have higher variance in the tails than in the center, which is what we would like to see there. All right, so much for, yeah, let's add a legend so just that we know what's real and what's fake. And that's the code example. So that hopefully gave you an insight in how to get started with neural nets and GANs. And that actually it's nothing too fancy, right? In the end, it's just a for loop that calculates some loss values, and based on that, you update some coefficients. And in the end, through the clever setup of like the loss function and the network architectures, you get an arbitrary target distribution that you might be interested in. So how can we use this? So as I said in the introduction, we can use this for multiple imputation, because that's exactly an example where we want to draw from like unknown distributions that we can describe with some covariates. and where we usually don't know like the functional form of the relationships between what we observe and what we don't observe. And therefore, like there is quite a few papers by now in the computer science literature that tries to tackle this. But usually they are only interested like with single value imputation. So they love to in-paint like missing pixels in images, but usually they don't want a distribution for that. But I tweaked it so that you can also do multiple imputation with those imputation nets. The architecture looks a bit more complex than the simple one. And that's of course due to the fact that you don't only want to input random noise, right? You also need to give as an input real data and also information about where your missing values are, because otherwise you couldn't find like those, you couldn't fill those holes. But other than that, it's not really more complicated than the GAN that we just looked at. It's just, in this case, it's one additional network and then 2 additional loss functions. But in the end, those are easy to calculate from like the network setups. And there's another competitor out there that uses like a couple more networks and a couple more loss functions. But in the end, also like with those basic building blocks, you could build this up as well. So let's see how well this actually does in comparison to, for example, Amelia. There's one simple experiment that is made up of like complete fake data, where we have like different types of variables that have missing values that we would like to impute, and different quantities of interest in the end that we would like to recover. And the missingness is set up in a way that if you would just remove, like if you would just do listwise deletion of any cases with missing values, it would bias your coefficient estimates. But what is like the more convincing plot, I hope, is that there is one like bimodal continuous variable in there that's not related to anything else. And I thought that like it should, like if you impute values based on this data, if you impute for this bimodal continuous variable, it should also at least sample from this distribution, from this bimodal distribution, right? And not from some other distribution where it actually might skew your like statistics as well. And that's actually what it does. So the dark solid line here is the actual distribution of this bimodal variable. Those dotted lines are what Amelia would do. And that's actually like, it makes Amelia really look bad, but that's actually what it's supposed to do. So that's not a flaw of Amelia. That's just how it is designed, because there's no other information in the other variables where it could make sense of like how to get those modes of this bimodal distribution. It can just sample basically from like this marginal normal distribution here, where it can infer the mean, and then unfortunately this would be at a point here where like it's very, very unlikely to actually have data points, right? So this could like screw up your statistics after imputation. So if you think of, for example, I don't know, ideology in the US right now, which could be bimodal, and if you impute missing ideology values with Amelia and there wouldn't be any information in the other variables, you would impute moderates quite a bit, which you probably don't want to do. And the generative adversarial net on the other side learns this distribution quite well. So even though there's no information in the other variables, it samples from the right marginal distributions here. The next application taking multiple imputation a step further and do small area estimation. Some of you probably did small area estimation with like multi-level regression post-stratification, or like the relatives with like any tree-based methods, but in the end they work very similar, but a bit different to what like a GAN would, how a GAN would work for this. So basically you can think of a small area estimation problem also as a missing data problem, right? So where you have your observations from your, like, let's say, nationally representative survey, and you know, for example, from a census where you have like the same demographic covariates in there, how those different like types of persons are distributed in your population or across different states, right? And then it would be for those that you don't actually get, like you don't actually ask them your survey, so you don't get their vote choice, for example, or whether they turned out in the last election or not. But yeah, so we can just put this to missing and make this a missing data imputation problem, right? And that's exactly what we do here. We reformulate like the small area estimation problem as a missing data problem, then use multiple imputation to impute values. And in the end, you would get like a filled out table for the entire population that you're interested in. And then you could calculate summary statistics for, like in this case, state 1 or state K, because you basically have every individual from your survey, from your census with like the imputed survey response. And then, yeah, you get those small area estimates. This is like, for those who are interested, like a similar plot or graph or formula, whatever, matrices for the multi-level regression post-stratification approach, which is not too different, but it thinks about it in like the other way around. So where you first want to make predictions for those types, and then you reweight those types based on your census sample. This is how the GAN matches up against like other competitors here, where we try to like estimate state level turnout. So this is also the classical like validation problem in many like multi-level regression post-stratification, small area estimation papers, because of course after an election you get turnout on state level. So you can have like the actual state level turnout on the x-axis, and the predicted state level turnout only comes from like a pre-election survey, nationally representative, with like the like a census where you then could reweight afterwards, like make those predictions and then reweight. This is how like the GAN approach does. Something weird is going on with MRP here. I'm not quite sure yet what, like it's shifted a bit like upwards. And like, since it's just a regression problem, you could just as well use Amelia as well, and impute those missing values and see how well that does. And this is Bayesian additive regression trees that can also be used for. And also there's, I'm not quite sure what is going on, where the shift is coming from. But that's what I got when using like the code of like, I guess it's a PA paper. So we'll have to look into that, but GAN works pretty well out of the box, and there's a table to show you that this is actually not just our visual feeling, but that the root mean square error is the lowest across all methods, and the correlation between actual turnout and predicted turnout is also quite like the best out of those, and quite decent. Next is the last application, where this slide is actually a conference poster that will be presented next week, I guess, where basically you can think of synthetic data as taking multiple imputation even more to the extreme, where you not only, like in the example of small error estimation, have like entire variables that are missing for entire groups of people, but where you have a target population where everything is missing, right? So basically that's, yeah, how you can think about synthetic data. You just want to make synthetic copies of some distribution and retain like the statistical properties of your population distribution, of your sample distribution as good as possible. Now, at first, you might think that this might be enough already, like running the GAN, just like we did in this coding example, running the GAN, and then just releasing like those synthetic data points instead of the real data points. This might be enough to actually protect privacy of your individuals in your survey. But unfortunately, that's not the case. Because you could think of a GAN like that is of infinite capacity that just memorizes your original data and then prints out random subsets of your data when you sample from it, right? So if your GAN would heavily overfit to the data, it could be the case that it is actually printing out actual data without you realizing that. So therefore, just synthesizing the data is not quite enough to protect privacy of individuals if that was your goal. However, there is a like cool framework and a clever way of how you could actually make it private, like you could protect the privacy by adding noise during the training, right? So if you add noise during the training, like you cannot overfit anymore. And if you can't overfit and you can only learn like higher abstractions of your data, you can prevent this like failure case of memorizing perfectly memorizing examples. And there is a principal framework that is called differential privacy that actually guides how much noise you will need to protect privacy to some like pre-chosen level of privacy that you want to achieve. So basically, as a researcher, you can turn the knob like of how much privacy do you want to achieve in terms of a mathematical guarantee. And then depending on the level that you want to achieve, this will guide how much noise you will have to add during training to prevent, to learn those like idiosyncrasies of your data. So as you have seen, however, with the GAN training before, it was oscillating a bit, right? So it's hard to tell like when to stop, because also we're not maximizing or minimizing, but we're hoping to achieve this equilibrium. So it's really hard to tell when to stop even without noise during the training. And then even if we stop, like it might be the case that a few iterations before we would have gotten a better representation of our data. With noise, this problem becomes even more difficult, right? Because with noise, this oscillates quite a bit more because we only have like noisy updates at every iteration. So what our observation was then is that you can actually use the sequence of generators and reweight them in a clever way to come up with a better like average generated data distribution, right? And you can reweight them because basically what you want to achieve after you've trained the sequence of generators is you are playing another zero-sum game, basically, where you want to find like the best combination of discriminators and generators post-GAN training. So that's also where the post-GAN boosting comes from. So what you can see here is like a bit more complex real data than before, also just two-dimensional, where you have like those 25 clusters of multivariate normal distributions in 2 dimensions that all have like the same variance, but however, like arranged on this grid. So the cluster means are like distributed in this 2-dimensional space. This is what the last generator would learn, even without privacy. Like it would it actually has a hard time due to the architecture to learn those disjoint clusters. So there will usually be some weird connections between those. And with this post-GAN zero-sum game, you can actually reweight like those samples in a clever way so that you get something that looks a lot more like this initial difficult distribution. With privacy, what you can see here is like the last generator didn't learn anything useful, or maybe it learned like that in this area here, there's something, but it didn't learn anything about like the rest, right? And this is very, very high noise. So this would be very privacy protective if those were our data points. And if we do make use of the sequence of generators that we trained, we can actually reconstruct a like better picture of the actual data distribution. However, it looks really noisy here, and that's of course what we would expect since we actually added noise during the training and made life harder. And now, like fine-tuning this, like finding a good trade-off between utility, so that it really still looks like something that it looked like before, and privacy is really the hardest bit in this kind of setup. We also applied this to actual census data from the US on the like census microdata, where if you want to go into it, can see that like this averaging across those generators actually gives like the best representation of some marginal statistics, like the distribution of different race self-descriptions in the census, and also like for the regression coefficients, or for the regression predictions as compared to when they were trained on real data. And the second case where you only had access to the privacy protective private synthetic data. So exactly that case that was also my motivating case for synthetic data, that sometimes you have to share like some data for reproducibility, but you cannot actually share information on the subjects that you had in your survey. So this is some initial results that make us hopeful that like in 3 years, remember how like the voice generation improved over 3 years. So in a couple of years, this will be hopefully really viable and cool solution for everyone to use. All right, so thank you very much for your attention. And I'm very happy to answer any questions or like brainstorm any new cool GAN ideas and like what you would want to do with it.
All right, thank you so much, Marcel. This was great. So the floor is now open for questions. I also posted the instructions on the different logistics that we can use for addressing questions to Marcel in the chat. While we wait for the first question from the audience, I may start the discussion with a question of my own. Namely, you talked about the search for the quest for the equilibrium in the min-max game, and that it can in practice never be achieved. So what are the criteria for convergence, if that is the correct word, that we should observe to know if our GAN application actually performed up to the standard that we needed to perform up to?
That's a great question, and there is not really a consensus on what you should observe then. So in a way, it depends on the particular loss metric you're using. So for example, for this KL loss that I've used in this tutorial, you can actually observe the KL divergence of the real and fake data. And the closer this is to zero, like the closer the distributions are. So that's something you could observe for this particular application. What computer scientists often do is they look at, like they eyeball the visual quality of their cat images, and then they are like, yeah, well, this looks like a cat, we're done with training. And came up with like sophisticated measures. They're called inception scores and inception score distances, where they use basically another neural net to embed like their pictures, and then they look at how different like this embedding distribution is from actual pictures of the same category. And with that, like they get a number on like this, what yeah, like previously was done as eyeballing images. But other than that, like for our purposes, we're probably more interested in also how well it retains statistics that we might be interested in, that we might be interested to retain. And they might be of arbitrary complexity, right? So it is a hard problem, and it is also conceptually not too easy to think about, like what quality actually means in the context of synthetic data.
All right, thank you so much. We're still waiting for questions from the audience, so let me ask you another one. Connecting the first part of your talk to the more applied side, especially with a focus on the social sciences, you first talked about the very obvious and apparent ethical concerns that go along with the generation of synthesized voice, video, or images. And obviously, the potentials for unethical conduct are apparent. And if we extend this to the social sciences, there's obviously the same idea that synthetic data could be used unethically, in the sense that you could produce fake data in line with theoretical expectations, and it might not as easy to catch up on your doctoring of the data. But over and beyond that, do you see any major ethical concern that could arise from the use of GANs in social scientific research?
That's a great point you raised, like with like the idea of forging data for your research needs. I've never thought about it that way, but of course this could be a problem. However, since it's not like you turn some knobs and then you say like, this is what my data should look like, because you actually, as the GAN is learning by comparison, right? You actually need the data that you want to work with. And then you could, if you were forging that, like you don't actually need a GAN, like you could just use the initial forged data that you have drawn from some distribution. Yeah, other than that, like, I guess, and that's also coming in with the privacy part. I think that, and that's not just GANs, but also other like machine learning techniques, or also our statistical methods. There is always an inherent like privacy threat, where like through inference we could uncover something about persons that they don't want anyone else to know, right? And imputation is one particular application of that, actually. So because it might be that people didn't answer a question because they didn't want to share with anyone. However, if we now can arbitrarily, well, from other data, infer what they most likely would have answered, by doing this inference, we could like threaten the privacy of those individuals that on purpose didn't answer the question to prevent this. So yeah, so that's a good question. And I think we should think as social scientists or as data-driven social scientists more about how to protect privacy or how to find principled ways to solve those problems and to work with those problems. And differential privacy is like a great start in that direction, in a way like that it also would prevent this kind of inference threat, because also if you would impute with differential privacy, you would need to add noise so that like you would be uncertain about, like even if your algorithm without noise would be very certain about a particular value that you would impute. With the noise, it would make it unlikely, or it would protect the privacy there. Yeah, but I guess that goes beyond GANs, like my answer to your question. But it's worthwhile to think about these questions also in these contexts.
Thank you. That's actually a great point that I'd like to get back to. When dealing with this approach that you presented for privacy respecting synthetic data, that obviously appeals to a lot of people, myself included, because I work with georeferenced survey data, which are obviously restricted access and couldn't be shared even with journal replication teams, which may be a problem if the journal that you'd like to submit to has a replication policy. But realistically speaking, if you have a data set, it's large N, large T, large K, so many observations, many time points, many variables. What would be the computational resources and the approximate effort that it would take in terms of setting up the GAN that could perform the synthetic production of such data? Is that something that we could credibly do with local resources, or is that rather something that may be feasible in the distant future?
Somewhere in between. So hopefully feasible in the close future. But yeah, so, and that's also, I guess, part of what I see as what I want to do with my dissertation and also my research after that. The problem is that computer scientists, they are very state-of-the-art driven and do not really think about particular applications. For example, like the least or the last application they would want to think of is like for social scientists, right? They probably don't even know that they are social scientists at a university as well. And that makes it really hard to implement those things for us, because often it's some like very like untidy GitHub repo, like where you need to try to find like the magic order of running scripts to get everything to work. And then it often only works for this particular benchmark data set. And as soon as you pass in your own data, it just fails. However, I think that was the same for like for the beginnings of Amelia and the like, right? So it's not like multiple imputation was developed in the 80s, but it wasn't until like the 2000s, until the rise of like, I guess, more stats like savvy social scientists, and also the availability of good enough, let's call it good enough software for those purposes, that it was actually used widely, right? And I think the same thing will happen here. So there needs like a lot of translation work to be done, but to cater between like the interests of computer scientists and statisticians and applied researchers. But I think that it would be a worthwhile goal, and it is my worthwhile goal, to get like a good enough implementation for a wide range of usual social science use cases. How well that works, yeah, that needs to be seen in the hopefully not too distant future.
Sounds great. I guess many people will be looking forward to that. So that's my list of questions. How about our audience? Do we have any more questions here? If that is not the case, Marcel, is there anything that you would like to add?
I would like love to hear all the ideas you have after like hearing this talk, and like would also like be very happy to hear those ideas via email or like any other mode of communication that you might get in touch with me. And yeah, like looking forward to also see your applications of this stuff in the not too distant future. And the other question, of course, is there anything happening in the US that I didn't get in the last like 70 minutes?
I think we can get back to that question in 2 minutes. So thanks, Marcel, also for offering people to get back to you with questions.
Right, so especially for the code bit that will be uploaded to the Data Lab GitHub, like I know that it can be frustrating, and I hope that I'm not one of those messy computer scientists where you like can't quite figure out how to get it to work. So like if you have any questions or troubles, let me know, and we will get this started.
So these materials will be posted on our GitHub. That's github.com/social science data lab shortly. And the Social Science Data Lab will be back in 2 weeks on November 18th, this time at 3:30 p.m. Central European Time, with a talk on open science with the Renku platform by Christine Chouara and Emma Jablonski. So hope to see you then. Thanks for your attendance today, and bye-bye. Thanks, Marcel, so much once again for your talk.
Thank you.